So let's take a look at just some very, very basic ideas of how to solve differentials and then also what their solutions would look like. So for each of the following differential equations, decide which diagram illustrates the general solution, then trace the curve that satisfies the initial value. All right, so we start off with this really basic DE. This f prime of x equals 3x squared. F at 1 is equal to 1. All right, so let's do this. We know that to undo a derivative, we take the integral. So we're going to integrate f prime of x with respect to x, and that'll just give us f of x. All right, so that's what this side is. So we just integrated that, and that's our fundamental theorem of calculus part 2. And then we're going to integrate 3x squared with respect to x, and that's an easy one. Remember, to take the antiderivative, you just add 1 to the exponent, and then you divide by the new exponent. There's also a constant of integration, okay? So don't forget that from Calc 2. And so what we end up with is that f of x equals x cubed plus c, okay? Now, this is the general solution. All right, so remember we talked about general and we also talked about particular solutions. So that's our general solution. And of the 4 graphs, the only one that clearly looks like a cubic is going to be the first one. Okay, so this is the graph that we choose. All right, so let's just box this one. All right. However, what is the particular solution? Okay, so in other words, which of these is going to be the one that we're going to select? So there's a couple ways to do this. One of which is we can just look for the one that contains the point 1, 1. All right, so we know that if we look up here, this means that x equals 1, y equals 1. All right, and so the only one that contains 1, 1, if this is the point 1 right here, we just trace it over, and it looks like right here would be the point 1, 1 approximately. So it's probably going to be this curve. Okay. Another way to do that is to just immediately substitute back into the general solution. So we know that since f of x is equal to x cubed plus c, this would imply that f of x is 1 and x cubed is 1. Okay, or x is 1, excuse me. So we get 1 equals 1 cubed plus c. And that's evident that c is going to be equal to 0 by subtracting 1 from both sides. All right? So the particular solution to this differential equation is f of x equals x cubed plus 0, or just x cubed. And we know x cubed passes immediately through the origin. All right? So the one that we would pick is going to be the one that goes right through the origin, which also contains the point 1, 1. As best as I can trace it. Sorry about that, it's a little bit tough to draw on the screen sometimes. And so that's going to be the solution that we trace. All right, so hopefully that makes sense to you all. It's not meant to be too difficult. Just a second example to reinforce that. So this time we have g prime, a different function, is equal to 2x plus e to the x squared. Right? So again, what we'd like to do is we'd like to be able to find the antiderivative of that. Okay, so g of x is going to be equal to the integral of 2x e to the x squared dx. All right. Now, unfortunately, this one's not as easy as the previous. Okay, so the last one we just had a regular old polynomial. So we have to go back to our Calc 1 and our Calc 2 to remember some of the techniques of integration. And this one's actually fairly easy because it's a u substitution. Remember, with a u substitution, you let u be equal to generally the composed function. All right, so basically if there's a function within a function, or in other words, f at g of x, usually let u be equal to g of x, the internal function. So let's let u be equal to x squared. The derivative of x squared, 2x dx. And that's perfect. That's exactly what we want. So we're going to replace 2x dx with du, and we're going to replace x squared with u, and we're going to see that we get a very basic integral. So this now becomes e to the u du And we know that when we integrate e to the u, that's just going to be e to the u plus c. And then finally, we just back substitute for u. So we get that our general solution, g of x, equals e to the x squared plus c. And again, that is our general solution. However, if we want the particular solution, we know that when x equals 0, y equals minus 5. So all we're going to do is just substitute. Okay, so we go down here. We're going to get negative 5 equals e to the 0 squared plus c. Or in other words, negative 6 is equal to c. Right? And remember, e to the 0 is 1. If we subtract 1 from both sides, we get negative 6. So the curve that we're looking at particularly is g of x is going to be equal to e to the x squared minus 6. And this is our particular solution. Now with the particular solution, we just go and we figure out what e to the x squared looks like. Right? And probably what we would like to do is we'd like to plug that into our calculator just to see essentially what e to the x squared looks like. I'm going to do that while we're going through. So make sure you have your graphing calculator handy. So I'm going to say e to the x squared minus 6. Then I'm going to graph that. All right. And you might have to resize the window. I had to zoom out just a little bit on mine. And I get this concave up parabolic relationship. Right? So it looks like to me the best choice is going to be, for the family, it's probably going to be this family right here. Right? And if I was to go through and try to select one of these, now remember, the point that we have is 0, negative 5. So it should pass through exactly this point right here. Right? And then when I also graphed it in my calculator, I did a trace on it, and I noticed that 0, negative 5 was a point on my function. So indeed, it is going to be that shape. Right. So these are two very rudimentary examples of being able to solve differentials. Right? And that's really nice when they just have like f prime equals or g prime equals. Most of the time, that's not going to happen. All right. So now that we know what the family looks like, we know what the particular solution looks like, and we know some basic techniques, in the next series, what we're going to do is we're going to be looking at what it looks like as the actual differential equation, not the solution. So these are the solutions of the differentials. However, what does the differential look like? So that's one thing we're going to be looking at. And then we're also going to be looking at being able to identify some of the fundamental characteristics of what the graph produces.